Listening practice, a refined and detailed version of your preface, acknowledgements, and list of symbols and abbreviations sections for the Structural Engineering Laboratory book. Structural Engineering Laboratory Preface. Structural engineering is a discipline that relies heavily on experimental validation to ensure the safety, durability, and efficiency of constructed systems. The Structural Engineering Laboratory serves as a bridge between theoretical principles and real-world applications, enabling students, researchers, and practitioners to verify design assumptions, assess material behavior, and innovate new construction techniques. This book is designed as a comprehensive guide for undergraduate and graduate students, as well as laboratory instructors and practicing engineers. It covers fundamental testing procedures, advanced experimental techniques, and the latest industry standards in structural evaluation. Emphasis is placed on hands-on learning with step-by-step laboratory procedures. Safety protocols to ensure risk-free experimentation. Integration of computational and experimental methods for accurate data analysis. Case studies demonstrating real-world applications of laboratory findings. Whether used as a textbook or a reference manual, this work aims to foster a deeper understanding of structural behavior through empirical observation and critical analysis. Acknowledgements. This book would not have been possible without the contributions and support of numerous individuals and institutions. We extend our sincere gratitude to colleagues and researchers who provided valuable insights and technical reviews. Laboratory technicians and staff for their assistance in conducting experiments and maintaining equipment. Students whose curiosity and questions helped refine the clarity and practicality of this work. Professional organizations, such as ASCE, ACI, ASTM, and ISO, for establishing the standards referenced throughout. Family and friends for their unwavering encouragement during the writing process. We also acknowledge the pioneering work of structural engineers and material scientists whose innovations continue to shape the field. Any errors or omissions remain the sole responsibility of the authors, and feedback for future editions is warmly welcomed. List of symbols and abbreviations. Symbol meaning unit F _ C compressive strength of concrete MPa, Psi, F _ Y yield strength of steel MPa, KSI, E modulus of elasticity GPa, Psi, epsilon strain sigma stress MPa, Psi, delta deflection / displacement in, lambda load factor phi resistance factor. Abbreviations, ASTM American Society for Testing and Materials, ACI American Concrete Institute, NDT. Non-destructive testing, LVDT Linear Variable Differential Transformer, FRP Fiber Reinforced Polymer, via Finite Element Analysis, UT Ultrasonic Testing, RC Reinforced Concrete, HPC High Performance Concrete. Notes, the preface sets the tone, explaining the book's purpose and audience. Acknowledgements recognize contributions while maintaining professionalism. Symbols / abbreviations are organized for quick reference, with units aligned to international standards, SI followed by imperial in parentheses. Would you like any additions, e.g., more symbols / abbreviations, or a dedication section? Here's a well-structured and detailed Chapter 1, Introduction to Structural Engineering Laboratory for your book, with expanded subsections to ensure clarity and depth. Chapter 1, Introduction to Structural Engineering Laboratory 1.1 Role of Laboratory Testing in Structural Engineering. Structural engineering relies on laboratory testing to validate theoretical models by comparing experimental results with analytical / numerical predictions. Assess material properties, e.g., concrete strength, steel ductility, for compliance with design codes, ACI, ASTM, Eurocodes. Evaluate structural performance under loads, static, dynamic, cyclic, to identify failure modes. Innovate new materials / techniques, e.g., fiber-reinforced polymers, self-healing concrete. Support forensic investigations after structural failures. Case example, testing full-scale beam column joints to improve seismic design provisions. 1.2 Safety Protocols and Laboratory Ethics. A personal safety, PPE requirements, hard hats, safety goggles, gloves, and steel-toe boots. Emergency procedures, locations of fire extinguishers, eyewash stations, and emergency shutoffs. Hazard-specific protocols, handling heavy loads, high-voltage equipment, or chemical agents, e.g., curing compounds. B. Equipment safety, load limits for frames and actuators. Electrical safety for data acquisition systems. C. Ethical practices, accurate data recording, no fabrication/falsification. Proper attribution of prior work in reports. 1.3 Calibration and maintenance of equipment. A. Calibration, purpose, ensure measurement accuracy, e.g., load cells, LVDTs, strain gauges. Standards, traceable to NIST, US, or equivalent bodies. Frequency, pre-test calibration and periodic checks. B. Maintenance, hydraulic systems, check for leaks and fluid levels. Electrical instruments, inspect wiring and connectors. Documentation, logbook for calibration dates and malfunctions. Table 1.1, Example calibration schedule. Equipment calibration frequency standard load cell biannually ASTM E74 LVDT annually ISO 9001-1.4 Data acquisition and analysis techniques. A. Data acquisition systems, sensors, strain gauges, accelerometers, thermocouples. Hardware, NIDAQ, HBM Spider 8. Software, LabVIEW, MATLAB, Python scripts. B. Data analysis 1. Statistical methods, mean, standard deviation, confidence intervals. 2. Regression analysis, stress-strain curves, load deflection relationships. 3. Error analysis, identifying outliers and systematic errors. Figure 1.1, Workflow from sensor output to final report. Chapter Summary, Laboratory Testing Bridges Theory and Practice in Structural Engineering. Safety and ethics are paramount in all experimental work. Calibration ensures reliable data, maintenance prolongs equipment life. Modern data acquisition systems enhance precision and efficiency. Discussion questions. 1. Why might lab test results differ from finite element simulations? 2. How would you troubleshoot a load cell giving inconsistent readings? Further reading, ASTM E4, Standard Practices for Force Verification. OSHA Guidelines for Laboratory Safety. Key features, practical focus, emphasizes real-world applications, e.g., case examples, calibration logs. Visual aids, suggested tables/figures to break up text. Pedagogical tools, summary and questions to reinforce learning. Would you like to add a laboratory setup checklist or expand on specific equipment, e.g., UTM, shake tables? Chapter 2, Material Testing 2.1 Concrete Testing Compressive Strength Test, Cube/Cylinder, Objective, Determine the ability of concrete to withstand axial load standards, ASTM C39, cylinder, is 516, cube. Procedure, 1. Prepare specimens, 150 mm cubes or 150 x 300 mm cylinders. 2. Cure for 7/28 days in controlled conditions, 20 plus or minus 2 degrees C, 95% RH. 3. Test in compression testing machine at 0.15 to 0.35 MPa/SEC rate. 4. Calculate strength equals peak load/cross-sectional area reporting, include curing conditions, failure mode, cone/shear, and strength variability. Split tensile strength test. Objective, measure indirect tensile strength standard, ASTM C496. Key formula, tensile strength equals 2P/pi LD where P equals load, L equals length, D equals diameter. Flexural strength test, modulus of rupture. Methods, third point loading, ASTM C78, center point loading. Significance, critical for pavement design. Non-destructive testing method. Principal application rebound hammer, ASTM C805, surface hardness correlation in situ strength estimation ultrasonic pulse velocity, ASTM C597, wave propagation time homogeneity assessment 2.2 steel testing tensile test standard, ASTM E8 key parameters, yield strength, 0.2% offset method, ultimate tensile strength, elongation percentage, modulus of elasticity stress strain curve analysis, identify elastic region, yield plateau. Strain hardening hardness tests test indenter load application Brunel, ASTM E10, 10 mm steel ball 500, 3000 kgf softer metals Rockwell, ASTM E18, diamond cone / steel ball 60 to 150 kgf hardened steels impact tests Sharpie vs IZAD, specimen orientation, horizontal / vertical, notch type, V-notch common, transition temperature determination 2.3 aggregate and cement testing sieve analysis, ASTM C136, purpose, determine. Particle size distribution key terms, fineness modulus, gradation curves, gap graded versus well graded aggregates specific gravity and water absorption, ASTM C127/C128, pycnometer method steps, 1 measure dry weight, A, 2. Soak for 24 hours saturated surface dry weight, B, 3. Submerged weight, C, 4. Calculate, specific gravity equals A/BC, absorption percent equals, BA/A times 100 cement consistency, VCAT apparatus, standard, ASTM C187 normal consistency, amount of water required for 10 mm penetration setting time tests, ASTM C191, initial set, greater than or equal to 45 minutes, final set, less than or equal to 375 minutes. Chapter features 1. Practical tips, concrete testing, ensure proper end grinding for cylinders, steel testing, strain rate effects on yield strength, aggregate testing, oven drying temperature control, 110 plus or minus 5 degrees C, 2. Troubleshooting guide, inconsistent compressive strength. Check curing conditions, abnormal stress strain curve. Verify extensometer attachment 3. Case study, correlation between rebound hammer readings and actual core strengths for bridge deck evaluation 4. Safety notes, impact testing, use protective screens, cement mixing, dust control measures review questions, 1. Why is cylinder testing preferred over cubes in some standards? 2. How does carbon content affect steel's stress strain behavior? 3. What does a hump gradation curve indicate about aggregates? Upcoming link, these material properties form the basis for structural element tests in Chapter 3. Chapter 3, Structural Element Testing 3.1 Beam Testing, Flexure and Shear, Simply Supported Beam Deflection Testing Objective, validate theoretical deflection calculations under various load configurations key components, test setup with roller/pin supports, hydraulic jack or actuator for loading, LVDTs for deflection measurement, strain gauges at critical sections standard, ASTM C78, concrete, ASTM D198, wood, test procedure, 1. Apply 2-point loading, 3-point method preferred, 2. Record load deflection data at 10% increments of predicted failure load 3. Continue until either, serviceability limit, L/360 deflection reached, ultimate failure observed data analysis, compare experimental versus theoretical, Euler-Bernoulli, deflection, calculate effective moment of inertia, for cracked concrete sections, reinforced concrete beam failure modes common failure types, 1. Flexural failure, ductile, yielding of tension steel concrete crushing, preferred failure mode, gives warning, 2. Shear failure, brittle, diagonal tension cracks sudden collapse, more dangerous, no warning, 3. Bond failure, steel slips relative to concrete, common in poorly anchored bars testing considerations, Instrumentation, strain gauges on steel and concrete, crack mapping, use digital image correlation, DIC, safety, contain explosive concrete spalling. 3.2 Column testing, axial and eccentric loading, axial compression test setup, rigid testing frame with spherical seats, displacement control, 0.5 mm/min typical, failure modes, material crushing, short columns, elastic buckling. Slender columns, key measurements, load deformation response, lateral deflection at mid-height, concrete strain, embedded sensors, eccentric loading. Test purpose, study PM interaction eccentricity methods, 1 physical offset of load. 2 moment application via cantilever arm standards, ASTM C39, modified for eccentricity, data interpretation, plot interaction diagrams, compare with code provisions, ACI 318 Chapter 10, 3.3 Slab testing, load distribution and punching shear, load distribution test setup options, uniform loading, airbags, sandbags, point loading, hydraulic jacks, measurement techniques, deflection profile, multiple LVDTs, moment distribution, strain gauges in reinforcement, punching shear tests. Critical 4, flat slabs at column connections test configuration, isolated slab column specimen, concentric load application failure characteristics, conical failure surface, sudden loss of capacity prevention methods, drop panels, shear reinforcement, stud rails, 3.4 connection testing, bolted, welded, and pre-stressed, bolted connection tests. Test types, 1 single bolt shear tests. 2 bolt group behavior. Key parameters, slip critical versus bearing type, pretension verification, turn of nut method, welded connection tests. Common tests, tensile tests of weld coupons, fillet weld shear capacity defect detection, ultrasonic testing, die penetrant inspection. Pre-stressed connection tests. Focus areas, anchorage zone behavior, long-term pre-stress losses. Instrumentation, load cells in stressing jacks, fiber optic sensors for tendon force. Chapter features. Practical considerations, beam tests, account for self-weight in calculations, column tests, use safety cages for buckling specimens, slab tests, ensure uniform support conditions. Case study example, progressive collapse testing of beam column joints under column removal scenario. Safety protocols, energy release precautions for pre-stressed elements, containment for explosive failures, e.g., punching shear. Review questions, 1. Why is third point loading preferred over center point for flexure tests? 2. How does slenderness ratio affect column failure mode? 3. What instrumentation would you use to monitor bond slip? Upcoming transition, these element tests provide the foundation for advanced testing methods covered in Chapter 4. Chapter 4, Advanced Structural Testing Techniques. 4.1 Shake table testing for seismic analysis. Experimental simulation of earthquake system components, hydraulic/pneumatic actuators, 6 DOF capability, real-time control systems, high-speed data acquisition, 500+ Hz sampling, model scaling considerations, Cauchy, fruit similarity, test protocols, 1. White noise tests, identify natural frequencies. 2. Sinusoidal sweeps, determine resonance behavior. 3. Historical ground motions, El Centro, Kobe, Chi-Chi records. Measurement techniques, optical tracking, DIC, laser vibrometers, inertial measurement units, IMUS, base isolation effectiveness evaluation. Case study, UC Berkeley's Pier Center tests on bridge pier retrofits using scaled Northridge earthquake motions. 4.2 Fatigue testing of structural components. High cycle fatigue evaluation. Test configurations, rotating bending machines, up to 10 cycles, servo hydraulic systems, 100 Hz. Capability, resonance-based systems, 200+ Hz. Key parameters, SN curve development, stress ratio, R equals sigma_min/sigma_max, crack growth monitoring, ACPD, ultrasonic, standards, ASTM E466, metals, ASTM C1368, concrete, failure analysis, beach marking techniques, fractography, SEM analysis, industrial application, wind turbine tower base connection testing under 1.0 load cycles. 4.3 Buckling analysis of thin-walled structures. Instability testing methods. Experimental approaches. 1. Southwell plot method. Delta/PVS delta linearization for critical load prediction. 2. Digital image correlation, DIC, full field displacement mapping. 3. Vibration correlation technique. Frequency shift vs load relationship. Specialized fixtures, Coiter's rig for imperfection sensitivity, combined loading frames, axial and shear, post-buckling behavior, mode jumping phenomena, energy methods for stability assessment. Aerospace application, composite fuselage panel testing under combined compression and shear. 4.4 Strain gauges and load cell applications. Precision measurement systems. Strain gauge technology, selection criteria, gauge factor, typically 2.0 to 2.1, temperature compensation, dummy gauges, grid configuration, rosettes for biaxial stress, installation protocol, 1 surface preparation, ISO 8501-1 SA 2.5, 2. Adhesive selection, cyanoacrylate vs epoxy, 3. Protective coating application. Load cell types, type capacity accuracy S-beam 5 to 500 knots plus or minus 0.25% fs. Pancake 1 to 5 mn plus or minus 0.1% fs. Hydraulic 10 to 50 mn plus or minus 0.5% fs. Signal conditioning, Wheatstone bridge configurations, noise reduction techniques, shielding, filtering. Case example, real-time strain monitoring in Burj Khalifa's outrigger system during construction. Chapter features innovative techniques, hybrid simulation, combining physical and numerical models, wireless sensor networks for large-scale test. Safety considerations, containment for fatigue test failures, earthquake-rated restraints for shake tables. Data interpretation, rainflow counting for variable amplitude loading, modal analysis for dynamic tests. Review questions. 1. How does scale affect shake table test results? 2. Why is the Paris law important in fatigue analysis? 3. Compare Southwell and DIC methods for buckling detection. Emerging technologies * machine learning applications for test pattern recognition. Transition to Chapter 5. These advanced methods provide the foundation for non-destructive evaluation techniques covered next. Chapter 5, Non-destructive testing, NDT, and evaluation. 5.1 Ultrasonic testing, UT, principles and applications. Wave propagation fundamentals, pulse echo versus through transmission techniques, velocity measurement, V equals lambda f, attenuation analysis, dB/cm, equipment setup, transducer selection, 0.5 to 15 MHz range, coolant requirements, gels, oils, A-scan/B-scan/C-scan displays. Concrete testing applications, rebar location and diameter estimation, delamination detection in bridge decks. Thickness measurement of structural elements. Standard compliance, ASTM C597, ISO 1920-7. Case study, UT evaluation of post-tensioning tendon ducts in a cable-stayed bridge. 5.2 Radiography, X-ray and gamma-ray testing, radiation-based inspection. Comparative analysis, parameter X-ray gamma-ray -- source machine isotope, IR192, CO60, energy range 10 to 450 kV 0.1 to 3 MeV. Portability limited. High exposure time seconds minutes. Minutes hours. Weld inspection protocol, 1 source positioning, SFD calculations, 2. Film/digital detector placement. 3. Exposure time determination. 4. Image interpretation, ASTM E94, safety considerations, radiation shielding requirements, dosimeter monitoring, exclusion zone establishment. Innovation, real-time radiography for composite bridge bearing inspection. 5.3 Acoustic emission testing, passive monitoring technique. Key characteristics, frequency range, 20 kHz 1 MHz, parameters monitored, hits, energy, duration, Kaiser/Felicity effect analysis, structural applications, crack growth monitoring in steel bridges, corrosion. Activity detection, pre-stressing tendon wire break source location methods, one time of arrival, TOA, triangulation 2. Zone-based location 3. Waveform-based analysis standard reference, ASTM E1316 case example, AE monitoring during proof load testing of a historic truss bridge. 5.4 Infrared thermography for defect detection, thermal imaging techniques, active versus passive methods, active, external heat source, lamps, flash, passive, ambient temperature differentials, defect identification, delaminations, thermal anomalies, moisture intrusion, cool spots, voids in composites, quantitative analysis, thermal contrast. Calculation, time temperature curves, bridge inspection application, deck subsurface deterioration mapping, bearing condition assessment standard guidelines, ASTM D4788, ISO 6781, chapter features comparative NDT matrix, method, defect types, depth range, relative cost UT internal flaws 0-10 radiography volumetric 0 to 300 mm AE active defects 0-50 IR surface/subsurface 0 to 50 mm Field implementation guide, selection criteria based on material type, defect characteristics, accessibility constraints, emerging technologies, phased array ultrasonics, digital detector arrays, DDA, AI-assisted defect recognition, safety protocols, radiation safety officer requirements, ultrasonic coolant MSDS compliance, thermal imaging PPE, eye protection, review questions. 1. Compare time of flight diffraction, TOFD, with conventional UT2. Why is AE particularly suited for monitoring growing defects? 3. How does emissivity affect thermography results? Transition to Chapter 6. These evaluation methods provide critical data for correlating experimental and computational models. Chapter 6. Computational and experimental correlation. 6.1 Finite element analysis, FEA, versus laboratory results, validation and verification framework methodology. 1. Model development, geometry reconstruction, CAD to FEA, material property assignment, isotropic/orthotropic, boundary condition simulation. 2. Correlation metrics, displacement error, % equals, FEA, EXP/EXP times 100, modal assurance criterion, MAC, for dynamic tests, strain energy density comparison, common discrepancy sources, imperfect boundary conditions, material nonlinearity approximations, mesh sensitivity issues. Case example, composite beam analysis showing 12% higher stiffness in FEA vs experimental due to perfect bond assumption best practices, iterative model updating techniques, uncertainty quantification, Monte Carlo methods, benchmarking against ASTM validation standards. 6.2 Sensor integration, LVDT, strain gauges, accelerometers, optimal instrumentation strategies, sensor selection matrix, parameter LVDT, strain gauge, accelerometer range plus or minus 100 mm plus or minus 5000 mu epsilon plus or minus 500 G, resolution 1 mu m 1 mu epsilon 0.01 grams, frequency DC 50 Hz DC 1 kHz 0.1 to 10 kHz, installation mechanical mount bonded magnetic base synchronization challenges, sampling rate alignment, Nyquist criterion, timestamp accuracy, multi-system integration, e.g., NIDAQ with high-speed cameras, advanced techniques, digital image correlation, DIC, complementarity, fiber optic sensor networks, wireless sensor node deployment, data fusion. Example, bridge load test combining 120 strain gauges with 8 LVDTs at 200 Hz, sampling. 6.3 Statistical analysis of test data, reliability assessment methods, data processing workflow. 1. Outlier detection, Grubbs test. 2. Normality assessment, Shapiro-Wilk. 3. Uncertainty propagation, GUM method. 4. Confidence interval determination. Key statistical tools: ANOVA *** source variation decomposition, regression analysis, linear, y equals beta plus beta x nonlinear, power law fits for fatigue data, Weibull analysis, for brittle material failure. Experimental design considerations, sample size determination, Cohen's d, test-retest reliability evaluation, Bayesian updating approaches. Case study: statistical evaluation of 150 concrete cylinder tests showing 8% COV in strength. Chapter features. Practical implementation guide, via correlation checklist, 1 mesh convergence study. 2. Boundary condition audit. 3. Material calibration tests, sensor deployment protocol, Wheatstone bridge balancing procedure, accelerometer mounting orientation guidelines, environmental compensation techniques. Computational tools, Python scripts for automated data comparison, MATLAB toolboxes for statistical analysis, commercial FIA post-processors, ANSI, Abacus, quality control metrics, R superscript 2 values for model fits, signal-to-noise ratio thresholds, repeatability standard deviations. Review questions. 1. How would you resolve a 20% discrepancy between FIA and experimental natural frequencies? 2. What sampling rate would you choose for impact tests lasting 10 milliseconds? 3. When should non-parametric statistics be used instead of t-tests? Emerging trends, digital twin integration, machine learning for automated model updating, blockchain for test data provenance. Transition to final chapter. These correlation techniques enable practical applications discussed in Chapter 7's case studies. Chapter 7, Case Studies and Practical Applications. 7.1 Failure investigations of real structures. Forensic engineering methodology. Investigation protocol. 1. Initial assessment, collapse pattern documentation, photogrammetry, emergency response interviews, as-built drawing review. 2. Material forensics, core sampling, ASTM C42, metallurgical analysis, SEM/EDS, chloride/sulfate content testing. 3. Load path analysis, alternate path method for progressive collapse, first yield determination. Case study 1, Hyatt Regency walkway collapse, 1981, key findings, design change in hanger connection, 4x stress concentration at failed box beam, lessons, importance of connection details, need for independent design reviews. Case study 2, Champlain Towers South, 2021, failure mechanisms, punching shear at slab column joints, corrosion-induced section loss, 60% in critical areas. Testing methods, half-cell potential mapping, carbonation depth measurement. 7.2 Retrofitting and strengthening techniques. Intervention strategies. Concrete structures, technique application effectiveness. CFRP wrapping column ductility increases epsilon_cu by 300%. Steel jacketing axial capacity plus 40% load capacity. Abrogue method. Beam shear eliminates debonding steel structures, gusset plate reinforcement, anti-SB. Recommendations: fatigue retrofit, peening, hole drilling, bridge-specific solutions, external post-tensioning, link slab implementation. Innovative approach, shape memory alloy, SMA, dampers for seismic retrofits. Performance validation, load testing pre/post intervention, long-term monitoring, vibration, corrosion. 7.3 Innovative materials testing, FRP, high-performance concrete, fiber-reinforced polymer, FRP, testing. Characterization tests, 1. Tensile properties, ASTM D3039. Fiber orientation effects, strain rate sensitivity. 2. Bond behavior, single lap shear tests, digital image correlation analysis. 3. Durability, freeze-thaw cycling, ASTM C666, UV exposure chambers. Field implementation challenges, quality assurance of field installations, fire performance limitations. High performance concrete, HPC, evaluation. Advanced testing matrix, Property test method typical range comp strength ASTM C3970 to 150 MPa permeability ASTM C1202 to 1000 coulombs shrinkage ASTM C157 400 mu epsilon at 1 yr innovative mixes, UHPC, 180 plus MPa. Self-consolidating concrete, slump flow 600 mm, graphene-enhanced cement structural applications, thin shell architectural elements, accelerated bridge construction - chapter features decision-making framework, failure prevention checklist, 1 redundancy evaluation 2. Robustness quantification 3. Durability monitoring plan emerging technologies, 3D printed structural elements, self-healing concrete, microcapsule/bacterial, nano-modified construction materials ethical considerations, whistleblowing protocols, expert witness responsibilities, data transparency requirements review questions, 1. What forensic evidence would distinguish corrosion failure from overload? 2. Compare CFR-PVS steel jacketing for seismic retrofits 3. Why does UHPC require different testing protocols? Laboratory/field connection, mock-up testing before full-scale implementation, sensor embedding for smart structures final transition. These practical applications complete the structural engineering testing continuum from fundamental principles to cutting-edge innovations. Appendices Appendix A, Laboratory Safety Checklist Pre-test Safety Verification Personal Protective Equipment, PPE Safety Goggles, ANSI Z87.1 Compliant, Steel Toe Boots, ASTM F2413, Hard Hat, Type 2, Class E, Hearing Protection, NRR greater than or equal to 25 dB for impact tests, equipment safety, load frame hydraulic lines inspected emergency stop functionality verified guardrails installed for elevated tests fire extinguisher, ABC type, accessible material handling, MSDS reviewed for all. Chemicals proper storage of curing compounds dust control for cement/aggregates post-test protocols, energy discharge confirmation, pre-stressed elements, debris containment procedures data backup completed - Appendix B, sample lab report format standardized laboratory report structure 1. Title page, experiment name, e.g., RC beam flexural test, date performed, team members 2. Executive summary, less than or equal to 200 words, key objectives, major findings, practical implications 3. Experimental procedure, test setup diagram, CAD/schematic, instrumentation table, sensor type range accuracy - LVDT1 DC 50 mm plus or minus 0.1% FS4. Results analysis, raw data tables processed results, graphs with error bars, 95% CI, failure mode documentation 5. Discussion, comparison with theoretical values, error sources, quantified, ASTM/ISO compliance statement 6. Conclusion and recommendations - Appendix C, ASTM/IS/BS standards for structural testing essential standards reference concrete testing, ASTM C39, compressive strength, is 516, flexural strength, BSN 12390-3, hardened concrete test steel testing, ASTM A370, mechanical testing, is 1608, tensile testing, BS 7448, fracture mechanics NDT methods, ASTM E1316, AE terminology, is 13311, ultrasonic testing, BSN 473, qualification certificates specialized tests, ASTM D3039, FRP. Tensile properties, ISO 6892, high strain rate testing - Appendix D, conversion tables and formulas quick reference engineering data unit conversions, parameter SI imperial factor - stress MPa psi times 145.038 moment KNM LBFT times 737.562 deflection mm in times 0.03937 key formulas, 1 elastic deflection, delta equals 5 WL, / 384 EI, simply supported beam, 2. Buckling load, P_CR equals pi superscript 2 EI / KL, superscript 2, Euler's formula, 3. Dynamic amplification, DAF equals 1 / 1, F / F_N, superscript 2, material constants, concrete, E_C equals 4700 FC, MPa, steel, G equals E / 2, 1 plus new, appendix features practical tools, safety checklist, QR code linking to video demonstrations, report template, digital version with auto calculation fields, standards, hyperlinks to online databases, conversions, uncertainty propagation guidelines usage notes. 1 safety checklist must be signed before each experiment. 2. Report format aligns with ABET accreditation requirements. 3. Standards list updated to 2024 editions. 4. Conversion factors include significant figure rules cross-references, Chapter 1, Safety, Appendix A, Chapter 6, Data Analysis, Appendix D, all testing chapters. Appendix C instructional tip, use appendices as living documents, maintain version control for institutional adoption.